Welcome back to physics. We're going to go over a graphing question. I have a velocity time graph and we're going to answer the questions below. Number 1, what is the acceleration of the object from t is equal to 4 seconds? So from here to t is equal to 6 seconds. On a velocity time graph, to get our acceleration, remember we need to find the slope from t is equal to 4 seconds to t is equal to 6 seconds. Now, if you look at the graph, you might notice the dots don't really align with the grid lines as well. So getting the exact acceleration, the slope at these 2 points might be a little tricky. But let's extend our vision. Let's go and check. The slope is pretty much constant from t is equal to 2 seconds all the way to t is equal to 8 seconds. And if we take a look at those 2 points, these 2 points do have more defined coordinates using our grid lines. So why not use these 2 points instead of the ones in the middle? The slope that we get will still be the same as the slope in between t is equal to 4 seconds to t is equal to 6 seconds. Okay, I'm going to write down my coordinates over here. My coordinates here is 2 seconds at 8 meters per second. And here I have my coordinates being at 8 seconds. And I have here negative 8 meters per second. For number 1, we're going to find our slope. Our slope over here is our rise over our run, which is our change in velocity. So change in v over our change in t. Our change in v over here is our final, which is negative 8 meters per second, minus our initial, minus 8 meters per second, divided by the change in time, which we have is 8 seconds, minus our initial time, which is 2 seconds. This gives us negative 16 meters per second over 6 seconds. And if we put this on our calculator, 16 divided by 6, we get negative 2.6 meters per second squared. What I'll probably do with the rounding for this one is I'm going to round this to negative 2.7 because it's a repeated 6 meters per second squared. Roughly 2 to 3 significant figures. Let's take a look at 2. Number 2, what is the average velocity of the object of the entire trip? Now, be very careful. We notice that the acceleration in this entire trip is not constant. Okay? Because it's not constant, we cannot take our final velocity minus our initial velocity and divide it by 2. We cannot do that because acceleration is not constant. Therefore, you cannot use this one is equal to your final minus your initial divided by 2. You cannot use this one because your acceleration is not constant. There is another way for us to calculate average velocity. Remember, average velocity can be calculated using total displacement, total s, divided by total t. You may recall that to get the displacement from a velocity time graph, you need to find the area underneath your velocity time graph. So if we take a look at our area, this is spanning all the way from here, all the way from here, and this region under here. Okay, it's from your line to your x-axis. Here's a little shortcut we can take, though I'll show us the full steps anyhow. Notice how the area underneath this part of the graph and this part of the graph are equal. If we remember, the area underneath the graph has a sign. It can be positive or it can be negative. If this part over here is negative, this part here is positive, and they are of equal size, of equal area, they will cancel each other out. So I actually don't need to calculate the area underneath this part of the graph at all. All I need to worry about is the area underneath this region over here. But I will calculate each area just to go over the calculation steps. To get our total S, my total S is going to equal to my area underneath this graph over here. So I'm going to, the area underneath here, A1, A2, and the third color here, A3. That is to get my total displacement. So I have A1 plus A2 plus A3. If we look at A1, A1 looks like a shape of a rectangle. You need to know the area of a rectangle. This is our width times our length. We have 2 seconds times 8 meters per second. This gives us 16 meters, positive 16 meters. The area underneath this one is also positive. The difference in our time here is 3 seconds. From 5 seconds to 2, we have a difference of 3 seconds in time, here to here. And we're going to multiply this one by our triangle equation. We need to multiply by the height of our triangle, which in this case is also 8 meters per second. Our triangle equation, we have to divide this by 2, which gives us 12 meters in our second region. In our third region, if you go by default, well, the area underneath my second region and my third region is going to be the same, but just negative. You can do that. Or walking this one over, we have this as 3 seconds multiplied by, over here, is negative 8 meters per second, divided by 2 as the area of our triangle. Here we have negative 12 meters. So if we put all these numbers down in the bottom, over here, we have this one is equal to 16 meters plus 12 meters plus negative 12 meters, in which case these two cancel out. These two cancel out. This leaves us with our S total as 16 meters. If we put this back into our V average equation, this gives us 16 meters as our total S, total displacement, divided by our total time, which in this case is 8 seconds. And as a result, we get 2 meters per second. This is our average velocity. Going over this concept here, you cannot use your kinematics equations if your acceleration in your entire trip is not constant. Okay, that part is important. Last but not least, describe the motion depicted in the graph. We have t is equal to 0 seconds to t is equal to 2 seconds. Our object was traveling at a constant velocity of 8 meters per second. So here our object is gaining distance, is moving forward. Notice from in the middle region, when the object's going from 2 seconds all the way to 8 seconds, there is a particular point in the middle where the object makes a momentarily stop, even though it is decelerating. So in this case, our object is slowing down from t is equal to 2 to 5 seconds. From t is equal to 2 seconds to t is equal to 5 seconds, our object is slowing down. It's slowing down at a rate of, what was that? Negative 2.6 repeated meters per second. Okay? So because I'm saying it's slowing down, I don't have to put the negative sign in front of the 2.6 meters per second. At t is equal to 5 seconds, the object stops, makes a momentarily stops. Momentarily. So we take a look at our graph over here. Notice our object has a 0 velocity. So now it stopped for a moment. From t is equal to 5 all the way to the rest of the trip, to t is equal to 8 seconds, our object here is actually speeding up, but it's speeding up in a negative direction. It's speeding up in opposite direction. Opposite direction, also at a rate of 2.6 repeated meters per second squared. So the acceleration is the same, but notice it does stop in the middle and then moves backwards. That's why its total displacement isn't as much as you expected, because it started moving backwards. At 8 seconds, notice the graph takes a little hike all the way up to 0 meters per second. It exactly at 8 seconds, our object is immediately stopped. If you want to use the graph to tell a story, which you could, in a particular example, if you want to describe a soccer ball, perhaps rolling at a constant velocity, then approaches a hill, it rolls up the hill. As it's rolling up the hill, it slows down because it's fighting gravity at an angle, and then it makes a momentarily stop halfway up the hill. After that, it starts to roll back down, speeding up until maybe someone like Godzilla stops the soccer ball at the base of the hill, for example. Oftentimes when you get a graph, it's a good idea to kind of visualize what motion is happening to help you better analyze the graph. Hopefully this video was helpful in walking through you how to analyze a velocity time graph. Tune in to another example later on.